Greetings, everyone. Hello, and welcome back to another Math 104 lecture. Today, what we will be discussing are Chapter 1.1. Again, I'm going by book, the third edition. So if you have the fourth edition, I'm not sure what it's called, but we're going to be looking at linear equations in one variable today. So that's going to be the goal. Now, before we get going, I did receive a question from someone based off of the last lecture. And I was actually really happy to receive it. Number one, because it shows that, she was paying attention. Number two, because she was thinking abstractly. So if you ever have, questions that aren't specifically answered in the lecture, feel free, lob them my way. I'll be happy to answer them. So the question is, and the question is related to radicals or roots. Again, last lecture, right? So one of our properties said that if we have the square root, and sorry, I'm going to zoom out real quick. Whoa, there we go. Square root of xy, we know that we can break it up into the square root of x and the square root of y, right? And we can always go backwards. If we have two roots that have the same indices, right, or indexes, like here and here, then we know that we can just combine it into one larger root with that same index, okay? Those aren't zeros. I was circling the blank index there. Again, index should be 2, right? If it's a square root, that's if it's not visible, it's assumed that it's a 2. Okay, so we know that that property holds for multiplication. We know that it also holds for division, right? When we have the a fraction that's inside of a radical, we know that we can apply that radical to both the numerator and the denominator separately. And then, of course, we can go backwards, right? If the radicals have matching indexes and one's on the top and one's on the bottom, we can just combine it and say it's the radical of the whole fraction, right? So we can go backwards and forwards with it. So the question that I received is, okay, it holds for multiplication, it holds for division. Does it hold for addition and subtraction? So more specifically, if we have the square root of x plus y, will this give us the square root of x plus the square root of y? And I'm going to show whether the answer is yes or no for addition, and the same process can be applied for subtraction as well. I'm just not going to go through it. Okay, so what's best to do here, whenever you have a case like this, always ask yourself, well, why don't I just plug in actual numbers to help conceptualize this idea and see what happens when I plug in real numbers? So what I'm going to plug in are 4 and 9, because 4 is a perfect square, 9 is a perfect square. So I know that at least on the right-hand side, it should look pretty nice, right? So I'm just going to say let x equal 4 and y equal 9. Okay, so given what I just wrote, I'm just going to plug in my numbers and see what happens, right? So we have the square root of 4 plus 9, and then we also have the square root of 4 plus the square root of 9. Now on the right-hand side, we have, okay, well, square root of 4 gives us 2, and we have the square root of 9, which gives us 3, right? So we know that this is going to simplify on the right-hand side to just be 5. And on the left-hand side, we have the square root of 4 plus 9, so we get the square root of 13, and I'll just bring it down again, square root of 13. And you say to yourself, well, is the square root of 13 equal to 5? Probably not, right? And why do I say probably not? Well, we know that 5 is the same thing as square root of 25, right? Because we know that if we have the square root of 25, it simplifies down to be 5, right? Essentially, all I did here was, in my head, I just said, well, 5 is going to be the same thing as the square root of squaring it, right? I'm applying an exponent and taking that exponent away, but I'm just making this square root of 25, right? So now we just have to ask ourselves, is square root of 13 the same thing as square root of 25? And the answer obviously is no, right? These are not equivalent. So given that, we can then say this process will not hold. This is not correct. You cannot break up any root, not just a square root. You can't break up any root by process of addition. If you have an addition inside of a root, you can't break it up into each individual component with the addition still holding outside of it. And once again, this same thing for subtraction, right? So it doesn't work for addition. It also does not work for subtraction, because all subtraction is the addition of a negative number, right? That's another way to think about subtraction. So you can go through and try it with subtraction if you'd like, but point is that it won't work. Okay, So now that I've answered that, let's go ahead and actually get with the new material here. So again, we're talking about linear equations in one variable. What's that going to look like? Well, before we get to that, what I really want to talk about first is domain. Now, you've heard me talk about this a little bit over the course of the previous lectures. Whenever I wrote things like, say we had some kind of fraction, like I wrote like 1 over x, right? You would occasionally see me write a comma and say, okay, well, x is not equal to 0. Why did I do that? Well, I did that for the purpose of domain. The domain of a function or expression or equation, whatever you have in front of you, is wherever the variable is defined. So basically what this is saying is, if we look at 1 over x in this really quick example, we say, okay, well, 1 over x, this is going to work for almost any value of x, right? If we plug any number in for x, or almost any number in for x, it should still be a fraction, right? We plug -2 in, we get -1/2. We plug a 3 in for x, we get 1 over 3, right? So it's a defined, expression for almost any number that we plug in. But if we plug in 0, we get 1 over 0. And we know that when we have 0 in the denominator, when we try to divide by 0, it's undefined, right? There is no answer. We can't conceptualize that. That's, it's gone. It blows up. So 1 over 0 doesn't work. So that means x cannot be equal to 0. Okay. So that's the definition of domain. The second definition, and the only other definition for the purpose of this lecture is solution. So a solution of an equation is the value or set of values that satisfy the equation. So given both of those definitions, let's go ahead and look at our first equation. So for our first equation, we have 2 over x minus 3 is equal to 8. And what I want you guys to do, or what we're going to do together, is I want to find both the domain of this equation and also the solution of the equation. So let's go ahead and look at the domain first. Now, when you're talking about the domain of an equation, you have to consider both sides. So both sides of the equation, because you're working with the whole thing, right? So first we look at 8 and we say, well, 8 is a constant, right? So it doesn't really matter what happens to x. 8 is always 8. So we know that 8 is defined. So great. The blue part, the right-hand side, that's already taken care of. 8 is defined regardless. Now we look at the fraction, 2 over x minus 3. And we say to ourselves, oh, wait, we have a fraction. We know that our variable is in the denominator, right? So if our variable is in the denominator, we are going to have at least some number somewhere, probably, where it's not going to work. So what we have to do here is we have to set our denominator equal to 0. So we say, okay, x minus 3, I'm just going to set this equal to 0. And again, the whole purpose of this, what we're doing right now, is we're finding the domain. We're not trying to solve for the variable yet. We're just trying to find the domain of the equation. So to find the domain, or to see where it's not defined, we set the entire piece, the entire denominator, equal to 0, and we're going to try to solve for our variable. So the way that we solve for our variable in this case, we have an x minus 3 is equal to 0. I'm just going to add both sides. I'm going to add 3 to both sides, so I cancel with the -3. So when I add 3 to both sides, we get x is equal to 3, right? Because +3, -3 are going to cancel. Okay, so we have x is equal to 3. What does this tell us? This piece right here, x is equal to 3. What this tells us is if we plugged in 3 all the way back here at our original equation, if we plugged in 3 for x, we get 2 over 3 minus 3, which means we get 2 over 0. And hence, we have an undefined equation, right? 2 over 0, it doesn't work, blows up. Okay, so we can't do anything with it. So what this really tells us is that the equation is defined for x being almost any other number, literally any other number, except when x is equal to 3. And what we can do is we can write our domain, so our final answer for domain, that's an M, as, and if you guys remember sets, from -infinity to 3, but not including 3, right? We have a parentheses. We don't want to include 3. Unioned with 3 to an infinity. Again, still not including 3. So what does this tell us? Again, if we're reading this in terms of set notation, it's all the numbers that are, all the possible negative numbers all the way going up until we hit 3. And at 3, it breaks, right? At 3, we stop and we say we are not including 3. And then we union this with the other piece of all the numbers that are after 3 going up to positive infinity. So this here is our final answer for domain. And more than often, I would say, in fact, 99% of the time, when I ask you guys to give me an answer for domain, I want you to write it in the set notation. So I want you to write it with, the negative infinity, the, parentheses, unions if necessary, so on and so forth. Okay? All right, let's look at a second example here. Let's say, oh, I'm sorry, we actually never solved this. My mistake, sorry about that. So we still have 2 over x minus 3 is equal to 8. Okay, so to solve this, what we have to do is we have to say, okay, we have x minus 3 in the denominator. So what I want to do is I want to multiply by x minus 3 on both sides. What's that going to do? It's going to cancel with the denominator on the left-hand side, and I'll get an x minus 3 on the right-hand side, right? So what I'm going to do here is I'm going to multiply both sides by x minus 3. And now don't confuse this with something that we were doing before. Before, what we were doing when we were trying to change the appearance of fractions is we would multiply the denominator and the numerator by the same thing, right? So again, just off to the side here, say we wanted to change the appearance of 1/2. What we would do is we would multiply by something, right? The same thing, top over bottom. And what this would give us is 2 over 4, right? And we know that 1/2 is equal to 2/4. And so we were just changing the appearance without changing the value. In an equation, it's slightly different. What I want to do here is I have a division. I want to cancel that division. But whatever I do to one side of the equal sign, I also have to do to the other side, okay? So we are changing the value of the fraction, but we're not changing the value of the equation, because whatever we're multiplying to one side, we're also multiplying to the right, okay? So what ends up happening, we get this piece cancels, right? We're multiplying x minus 3. The x minus 3 would go to the numerator, hence it would cancel with the denominator, right? And that's by design. That's what we were trying to do. So what do we have on the left? We end up with a 2 on the left. And we have 8 times x minus 3. Our next step here is we want to distribute the 8, right? We want to try to get x by itself. So we carry the 2 down. We distribute the 8 to each piece. We get 8x minus 8 times negative 3 gives us a negative 24. Okay, we're still trying to isolate our variable here, so we're going to add 24 to both sides. We get 26 is equal to 8x. And then we're just going to divide by 8, right? So dividing by 8, we get 26 over 8 is equal to x, and we can simplify this one more time because we see that they're both even numbers, right? So if I'm pulling the 2 out of both pieces, we pull the 2 out of both pieces. If I pull the 2 out of the 26, I'm left with a 13, and if I pull the 2 out of 8, I'm left with a 4. So the 2 over 2 is going to cancel, and we know that this is just 13 over 4 is equal to x. And this here is our final answer. Okay, so now we've solved for x. We've also found the domain of the equation. So basically this is saying that the equation is defined for all numbers except when x would be 3. And here we know that the solution to the equation, x is equal to 13 over 4, 13/4. Okay, so now let's go ahead and move on. For the next part, we're not going to try to find the solution. We're only going to try to find the domain. So to find the domain of this equation, we have square root of x plus 8 is equal to 16. Okay, so again, to find the domain of this, we have to ask ourselves, okay, the purpose of domain is figuring out where this equation won't work, okay, where this breaks, where we can't possibly evaluate it, right? So we say to ourselves, okay, well, what do we know about square roots? What do we know about all even roots? If we have a negative number inside of an even root, it breaks, right? Same way that if we have a 0 in the denominator of a fraction, that it would break. So we are trying to find out where this piece right here, the x plus 8, would be negative. right? Because if it's 0, the square root of 0 is still 0. That's okay. If it's positive, we have the square root of a positive number. That's totally okay. But if x plus 8 comes out to be a negative number, then we have the square root of a negative number, and that's a complex number, and we don't want that, right? It breaks. We're only talking about real numbers here. So what we have to do here is we have to set this piece, everything that's underneath the square root. So again, I'll underline it. Everything that's underneath the square root, our radicand, we have to set that to be greater than or equal to 0. So what I'm going to do is I'm going to say x plus 8 is greater than or equal to 0. And before I continue, once again, we have 16 on the right-hand side. When we're talking about the domain of equation, we have to look at both sides, but 16 is just a constant, and for the same reason that we had it for the first example, we know that whatever x is, it's not going to change what 16 is, right? 16 is a constant. It's never changing based on x, so it's always defined. So we don't have to worry about the right-hand side. Okay, so we have an x plus 8 is greater than or equal to 0. So now all I have to do is just solve for my variable, right? So I'm just going to subtract 8 from both sides. So minus 8, and we know that then those are going to cancel, and we're left with x is greater than or equal to negative 8. So what does this tell us? This essentially tells us that, okay, if x is greater than or equal to negative 8, we will get a 0 or a positive number underneath the radical, right? So say we did have x is equal to negative 8, we would have negative 8 plus 8, and that would give us 0. We would have the square root of 0, and then bam, we're good, right? But if x is even slightly negative, so if x is going to be like negative 8.1, for example, well, if we did that, we would have negative 8.1 plus 8, and we would end up with a negative 0.1 underneath the square root, right? And then we have a negative number underneath the square root. The whole thing falls apart. So this again tells us that x has to be greater than or equal to negative 8. And writing this in set notation, we say, okay, it could be negative 8, right? We're including negative 8, so we're going to put a parenthesis, or I'm sorry, we're going to put a bracket, right? Bracket means that we're including the number. So we're starting at negative 8. And we also want all the numbers that are greater than negative 8, right? So this goes all the way to infinity. So this could be negative 7, negative 6, all the way, 24, 25, all the way to positive infinity. Any of those numbers would make this defined, right? So this will be our answer to domain. Okay? So hopefully that makes sense. Okay, so that's some examples with domain. Now I'm going to give you guys an opportunity to go ahead and try your hand at the first classwork assignment. So the first classwork assignment is find the domain of the following fraction. The following fraction is 16x all over 12x minus 4 is equal to 1. Okay, so try your luck at this. See if you can figure this one out. Again, you're trying to find the domain. Don't try to solve this. Just try to find the domain of it, okay? So pause the video, see what you come up with. Okay, so hopefully that wasn't too bad for you guys. So again, what we're trying to do here, we see that we have a fraction, right? And before we even evaluate the fraction, let's go ahead and talk about the right side. We have a 1 on the right side. We have a constant. Constant means that it's always constant, so we don't have to worry about the domain of that, right? It's always going to be 1. It's always going to work regardless of what x is. So we only have to focus ourselves with this fraction here. So now this is the first time that we've had the variable in the numerator as well, right? But ask yourself, let's look at a basic, just a really basic fraction. If we have like x over 3, does it matter what x is? If we have any negative number, right, and we put it over 3, okay, yeah, sure, we get a negative number, but it's still defined. If we have any positive number, it's still a positive number, and that's obviously defined. And if x is equal to 0, well, then we have 0 over 3, and we know that that would be equal to 0. So then it doesn't actually matter that our variable is in the numerator, right? So the x being multiplied against the 16 in the numerator, we actually don't even need to concern ourselves with that. That doesn't affect the domain. That doesn't affect where this equation can still be valued. So all we have to concern ourselves with is this piece here, the denominator, the 12x minus 4. So we find ourselves in, kind of what we were doing with the very first example. We're going to set 12x minus 4 is equal to 0. We're trying to find out where this breaks, right? So what I'm going to do is, okay, I have the minus 4. I'm going to add 4 to both sides. So that leaves 12x by itself, right? And adding 4 to both sides is going to cancel with the negative 4 on the left, and we get a positive 4 on the right. And now all I'm going to do is I'm going to divide both sides by 12. So dividing both sides by 12, I get x. I get 4 over 12. And we know that this is the same thing as 1/3. So x is equal to 1/3. Okay? And now what does this tell us? Again, if we're writing this in terms of domain, or I'm sorry, in terms of sets, we can say, okay, well, we know that all the numbers going up from the left, so all the negative numbers essentially coming up from the left to 1/3 would work, but 1/3 specifically is not going to work, right? So we have all the numbers coming from the left until we hit 1/3, and we don't want to include 1/3, so we write a parentheses. And then we also know that all the numbers after 1/3 are going to work as well. So we do the union. We're talking about all the numbers to the left of a third, all the numbers to the right of a third, but we don't want to include a third. Hence, we are not writing any brackets, right? So this would be our answer for the domain. And if we were to double check our answer, just to make sure that this is correct, right, we could plug 1/3 back into our denominator here. So I'm just going to clean this back up. Okay. So plugging 1/3 back into our denominator of 12x minus 4, what would happen? Well, if we plugged 1/3 in, so we would have 12 times a third. So 12 times a third, and we know that that's minus 4. We know that 12 times a third is the same thing as 12 over 3. 12 over 3 gives us 4, and we would have 4 minus 4, and 4 minus 4 is 0, right? So that would mean that at 1/3, at x is equal to 1/3, we would have a 0 in the denominator. Hence, we know that it can't possibly be included in the domain because our fraction would blow up. Okay, so we go ahead and clear that, and that's it. Hopefully that wasn't too bad for you. So now let's actually discuss the main meat of this lecture, which is linear equations. So a linear equation is going to be always in the form of ax plus b is equal to 0, where a is not equal to 0. And the reason a can't be equal to 0 is because a is the coefficient of our variable. So if a is equal to 0, we're essentially getting rid of our variable here, and then we would just be left with, you could essentially imagine it hypothetically as b is equal to 0, and I mean that's just nonsense, right? B is just some constant. So if b were like 7, for example, we would have a case where it's like 7 is equal to 0, and again, that means nothing, right? Okay, so we're always going to be in the form of ax plus b, where we have some coefficient of x plus some constant. Okay, now also keep this in mind, ax plus b is equal to 0. The power of x, the exponent of x, remember if the exponent is hiding, it's a 1, right? So the power of x is 1. So we can also, this equation is also known as a first degree equation because the power of x is 1. So when we talk about quadratics where, we have x squared, that will be known as a second degree equation, and so on and so forth. Okay, so that's coming up later, but just keep that in the back of your head. Now, one other thing to keep in the back of your head is this exponent. And I want you guys, I'm not going to really specifically talk about it, but if we have x to the first power, I want you to keep in mind of how many solutions we get for the equation. And then when we get to quadratics where we have x squared, I want you to keep in mind of how many solutions we have for those equations as well, okay? So we'll discuss that a little bit later as well. Okay, so there are 3 types of linear equations, and I'll write them all out. The first type is called an identity. Okay, an identity is where the equation, it's an equation where all real numbers will be solutions. Okay, so if you have, if we have an equation and then you can plug in any number for x and it won't impact the equation, then this would be an identity. Okay. We have a conditional. So a conditional. And a conditional is where only certain numbers will be a solution to our equation. So conditional, you think there's specific conditions that are applied here on your variable. So only specific numbers will be your answers. And then last but not least, we have inconsistent. Inconsistent equations or inconsistent linear equations are where you have no solutions. And if you have no possible solutions, what you would write is the same thing that we would write when we had no solutions for sets. We would write the empty set, right? The empty set is that circle with a dash through it. Again, just really want to hammer this in. You do not write the set of the empty set. That would be wrong, right? You just write the circle with the slash through it. Okay, so that's the only time that you're going to write the empty set for a linear equation is when there are no possible solutions. So let's go through and look at a couple examples. But before that, we should try to talk about how to solve them, right? That would make sense. So there's a methodology in how to solve any specific linear equation. And generally, it's in about 5 steps. Now, some of these steps I included because I'm going under the entire assumption that some of you have never seen a linear equation in your entire lives before this class. So they might be already pretty intuitive that you wouldn't even need to consider them a step, but for the purpose of this, I'm just including it just so you can keep it in the back of your head. So the first step is if you have fractions, you're going to multiply both sides by the LCM, the lowest common multiple, which means you're essentially just trying to clear the fractions. So step 1, clear fractions. Okay. Step 2, you're going to expand your terms if necessary. What do I mean by that? I mean, if you have some specific numbers inside of a parentheses and you have a multiple outside, expand means multiply, right? You're essentially distributing. So this basically just means distribute. Okay. Your third step is you're going to try to isolate your variable on only one side of the equation. The reason this is important is because sometimes you'll come across a linear equation where your variable is on both sides of the equation. So what that means is you need to either move the one on the right to the left or the one on the left to the right. So isolate variable. And again, we're all just going to have to deal with my absolutely terrible handwriting. That's why I talk over this, because if I didn't talk over this, you guys would see isolate squiggle and no one would have any idea what I'm talking about. Okay, fourth step is, whoa, hello. My pen stopped working. Okay, we're good. Fourth step is we are going to combine the terms. So we're going to combine the like terms. What does that mean? Well, remember when we did foiling, right? We would always end up with like some square number. We would always end up with a constant. But in the middle, when we foiled, we would end up with two terms that would always, combine together, whether you would subtract them or add them, right? We're looking for like terms and we're just going to put them together. So combine terms. Okay, and our last step here is solve for the variable. So solve. And what that means is once we've done the first 4 steps, or whichever ones are applicable, we then will have 1 or 2 final operations that are tied to the variable. We have to reverse those operations, right? So if we have a coefficient of a variable, if we have, for example, 3 times x, to undo the 3 times x, we have to divide by 3. So we're undoing whatever operation is still there. If we have an x plus 2, we have to subtract by 2, right? Okay, so that was a lot of talking. Let's now look at a real example so that we can, kind of dive into this. So solve for x, okay? We're trying to solve for a variable x. Say we have, our example here is 1/5 times x minus 2 is equal to x. And now we say to ourselves, oh, we have a fraction, we have our variable on both sides of the equation. What are we going to do? Again, our very first step here is clear the fractions, right? We're going to try to get rid of the fractions. So to clear a fraction, we have to multiply by the denominator, right? Now in this case, we only have 1 fraction, so our lowest common multiple is just going to be 5. But if, for example, we had a 1/7 as well, then we would have to multiply by 35. because we're multiplying by 5. We're also multiplying by the 7. So it's the same thing as multiplying by 35, right? But in this case, we only have the 1/5 to get rid of. So we're going to multiply both sides by 5. So multiply by 5, multiply by 5. Great. So what ends up happening? 5 times 1/5 is going to cancel, right? Because that's the same thing as 5 over 5, which is just 1. So on the left-hand side, I'm just left with x minus 2. On the right-hand side, 5 times x gives me 5x, right? Okay, so now what I have left to do is, well, we go through our steps, right? Do we have to distribute anything? No, right? We don't have to distribute anything. Do we have to isolate our variable? Well, yes, we do, right? Because we have the variable on both sides of the equation. And now, whichever way you want to subtract or like whichever way you want to move things over, totally up to you. Me personally, I avoid negative numbers whenever possible because I am prone to making sign mistakes, as I think we've seen already during one of our class meeting times. So I just try to, make life easy on me and say, okay, well, I'm just going to move the one singular x over to the right side, because if I move the 5x over, I'm going to end up with the negative 4x, and that's just going to be more annoying than it's worth, right? So I'm going to subtract both sides by x, and subtracting both sides by x, so minus x, and going forward, for the record, I'm not always going to write, when I say I'm subtracting both sides by x, I'm not always going to write minus x on both sides. I'll leave it that you guys understand what I'm talking about. But for the purpose of this video right now, I'm writing it here out. Okay, so minus x, that's going to cancel, right? And 5x minus x, I'm going to be left with 4x, right? If I have 5 of something and I take away 1 of that something, I'm left with 4 of that something. And our -2 just carries down, right? And so we go back to our steps here. Combine terms. Do we have anything to combine? And we say, nope, there's absolutely nothing to combine. So this is a pretty easy case. We skipped step 2 and we skipped step 4 because they were not applicable. But now we're at step 5, which is solve, right? So we have to look at our final operations tied to our variable. The last operation that's tied to our variable is this guy right here, right? We have a 4 times x. So to undo multiplication, we have to divide by 4. So we divide by 4 here. And whatever we do to one side, we do to the other, right? So we divide by 4, divide by 4. X is now by itself, which is exactly what we wanted. And we have -2 divided by a +4. We know that a negative number divided by a positive is still going to be negative. 2 divided by 4 is the same thing as 1/2. And now we have just shown that x is equal to 1/2. So now I'm going to ask you guys, think about this. We had 3 different types of equations, right? We had identities. We have 3 different types of linear equations. Let me specify. We had identities, we had conditional, and we had inconsistent, right? Identity is where all the numbers would be a solution. Conditional is where only certain numbers are a solution, and inconsistent is where we have no solutions, right? So having said that, which one would this be? Well, this one is going to be a conditional, because only specific numbers, or only a specific number, in this case, one number, is a solution, right? X equals 5 is not going to work here. If we plugged x is equal to 5 way back all the way up here, right, then this equation would not work. So for example, just saying 1/5 times, if x were equal to 5, 5 minus 2 is equal to 5, we would get 1/5 times 5 minus 2 is 3, so we would get 3/5 is equal to 5, and obviously that's nonsense, right? So we've just shown that there are some numbers that will not satisfy this equation, and in fact there's only one number. Whoa, how did I do that? There we go. Go back. Stay there. Okay, we only have one number where this is going to work, our -1/2, right? And we can go ahead and just the same way that I just plugged in 5 to show that that didn't work, we're going to do a check just to make sure that this does work. So we have 1/5 times, it was x minus 2, right? Oh man, yeah, x minus 2. So we have -1/2 minus 2 is equal to -1/2, right? And this should work out. We should end up with a -1/2 is equal to -1/2. That's the entire goal here, right? So, all right, it's a little annoying because we're dealing with fractions and negative numbers, but that's okay. So we have a -2 is the same thing as -2/1. I'm going to make that negative 4 over 2. And the reason being is because I want it to be able to add together or subtract with my negative 1/2. And this is still negative 1/2, right? And we bring the 1/5 down, okay. And we have, okay, negative 1/2. So we have a negative on the outside, and we have 1 minus 4 all over 2, okay? Because again, we have common denominator. We can just go ahead and combine the fractions, right? And then this sign would carry down, right? So that's just addition or subtraction of fractions, which hopefully you guys are acquainted with by now. Okay, so now we get 1/5 times, and this is going to be negative 5 over 2 is equal to negative 1/2. And what do we know is going to happen here when we multiply these fractions? Well, the 5 in the denominator is going to cancel with the 5 in the numerator, and all we are left with is a negative 1/2 is equal to negative 1/2. And we have just shown that this works for our solution. So our check worked, it worked out. I'm not always going to require you to do a check. There are certain situations where you do need to do a check, but for linear equations, 99% of the time, you do not need to do it. Okay, let's look at one more example here, and then I'm going to let you guys do the next classwork assignment on your own. So next example here, we have 2 times 3x minus 6 plus 5 is equal to 12 minus 19 in parentheses minus 6x close parentheses. Okay, so our very first step is clear fractions, right? Well, we have no fractions to clear, so great, skip that step. Okay, next step is, if I remember correctly, I erased everything, didn't I? That's unfortunate. That's okay. Our next step is expand the terms if necessary, right? So what can we expand here? Well, we have the 2 times that whole piece in the parentheses, and we have the negative sign being applied to the 19 and the negative 6x, right? So we're going to go ahead and we're going to expand all of these terms. So 2 times 3x and 2 times negative 6. Well, 2 times 3x gives us 6x. 2 times negative 6 is minus 12, right? And we bring down the plus 5. Okay, we haven't touched the 12, so we're just going to bring that down. And then when we expand, we're applying the negative to both of these values in the parentheses, right? Which means we're flipping the sign now of everything in there. So now we get a minus 19, and the negative of a negative 6x gives us a plus 6x here, right? Okay, so moving forward, now what do we have to do? We have to combine like terms, right? So what do we have that are like terms? Well, we know that we have a negative 12 and a 5. We can combine those. And we have a 12 and the 19. We can combine those as well, right? So we bring the 6x down here. Negative 12 plus 5. Well, it's a larger negative number than it is a positive number, right? So we know it's still going to be negative. So 12, it's the same thing as 5 minus 12 gives us negative 7. Over here, 12 minus 19 is also negative 7. And because of the commutative property of addition, I'm just going to put the 6x in front. Again, won't change anything. 6x minus 7. And you say to yourself, wait a second, these look very similar. One might even say they're identical, right? So if you were persistent and you wanted to keep going, you can say, okay, I'm going to add 7 to both sides. Okay, if we add 7 to both sides, we have 6x is equal to 6x. We are going to divide by 6, and we get x is equal to x, right? And we say to ourselves, oh, x is equal to x. Well, yeah, I mean, duh, right? It's the same number is equal to itself, right? So now we have just shown that this is an identity linear equation. And the reason is because x can be any number and not affect the total outcome. Let's go ahead and try one example of x being any number. Let's say x is going to be equal to, I don't know, a nice easy number. Let's say 2, right? So if x is equal to 2, then what I'm going to do is I'm going to plug in 2 wherever there's an x. So 2 times 3 times 2, because there was an x there, minus 6, plus 5, and is equal to 12 minus 19 minus 6 times 2 here. Okay, so now let's go ahead and just do our check. So 2 times 6 minus 6 plus 5 is equal to 12 minus, and now we have 19 minus 6 times 2. 6 times 2 is 12, right? But it's a negative 12. So 19 minus the 12 gives us a 7. So 12 minus 7 here. And what's 6 times 6 minus 6? 6 minus 6 gives us 0. So we know that 2 times 0, that's just going to cancel, right? Anything times 0 is just 0. So we're just left with a 5 here. And 12 minus 7 is 5. And once again, now we've shown, again, just for one quick example of x is equal to 2, that we still get back an identity. We still get back one side is equivalent to the other side, and it doesn't matter what x can be. Okay, so this is an example of an identity linear equation. Now, more often than not, I just wanted to make this quick remark here. Of the three of identity, inconsistent, and conditional, the one that you will see 90% of the time is conditional, where you are solving for a variable and only one specific solution, or however many numbers, only a specific number of numbers will satisfy the equation. Whereas in identity, it's all the numbers, and inconsistent, it's none of the numbers. Okay, so try your hand now at the second classwork assignment, which I will write out here. So you're going to solve 3x minus, and now we have a bracket, 2x minus, and then 6 times, and then in parentheses, x plus 1, close the bracket, is equal to 7x minus 1. And if you guys have never seen a bracket before in a mathematical expression or equation, all it essentially means is just treat it like an outside parentheses. We tend to use brackets instead of doubling parentheses just so it looks better, but it's essentially just more parentheses. So that's how you would treat it. Okay, so try your hand at it, see what you can come up with, and yeah, we'll talk about it in a second. Okay, so hopefully that wasn't too bad for you. So what are we going to do? Well, the first step is we're going to try to clear fractions. Are there any fractions? Nope, so skip that step. Okay, now we're going to expand, right? And it's helpful to expand from inside going outward. What I mean by that is do this piece first and then do the outside piece. Because if you try to do the outside piece first, it will work, but you are more prone to making a mistake down the road. You can do it. There's no harm in doing it. I'm just letting you know it's a little easier to do the inside pieces first. So what do I mean by that? Okay, well, 3x is just going to come down, minus, we're going to keep the bracket. We're not going to touch the 2x yet. This is the part that I'm going to expand first. So the -6 applied to each piece here. -6 times x and -6 times +1. So we get a -6x minus 6. And nothing is happening on the right-hand side, 7x minus 1. Okay, so now what I want to do is I want to combine my like terms inside of the bracket. You could also distribute the negative sign first, totally okay. I just see that I have a 2x minus a 6x, so I want to simplify that down first. So we have 3x minus 2x minus 6x gives us minus 4x minus 6 is equal to 7x minus 1. Okay, we're going to apply that negative sign to every piece throughout. So we have 3x, and now it flips the sign of the -4x, so we get a +4x, and it flips the sign of the -6, so we get a +6, right? And so we get 7x minus 1, and we're just going to condense it one more time. 3x plus 4x is 7x plus 6 is equal to 7x minus 1. And you say to yourself, okay, this is already looking strange. 7x plus 6 is equal to 7x minus 1. It doesn't really look like there's any number that's going to satisfy this. So let's go ahead and if you try to move, the 7x over to the other side, you're just going to be subtracting the 7x anyway. So we can do that. Let's subtract both sides by 7x. And if we do so, we end up with 6 is equal to -1. Is 6 the same number as -1? You ask yourself, and you're going to say, no, this is complete trash. This means nothing. Oh, there we go. This absolutely means nothing at all. So we realize that this is going to be an example of an inconsistent linear equation. And then you would just write, well, 6 is not the same thing as -1. There are no solutions to this equation because, again, inconsistent linear equation. We ended up getting 7x plus 6. And I'm just circling this not because it's my answer, because this is the main part of this that you should focus on. We got a 7x plus 6 is equal to 7x minus 1. And there's no real number that is going to make this true. You can try. You can, if you wanted to, you could essentially move the other numbers over. We didn't have to subtract the negative 7x, right? So if we wanted to, we could say, okay, 7x plus 6 is equal to 7x minus 1. And if you wanted to, what you could do is you can move the negative 1 over. Or you can move the 6 over. So let's move the negative 1 over. We have 7x plus 7 is equal to 7x. Let's divide everything out by 7, because we can do that, right? There's a 7 in front of everything. So divide both sides by 7. And if we divide both sides by 7, we get x plus 1 is equal to x. And you say to yourself, oh, yeah, no, it's pretty obvious that this is garbage because there's no number that is equal to 1 plus itself, right? If you have 0 for x, you can't say 0 is equal to 1. Right? So we've now shown that this is an inconsistent linear equation. So it doesn't matter what x is, the outcome will always be false. Okay, so let's go ahead and clear that. And that was your second classwork. Okay, so now what we have to do is we have to consider solving for a specific variable. What happens if we have more than one variable in an equation, but we only actually care about one in particular? So let's say I give you 3x plus 6y is equal to 9. And I say to you, I only want you to solve for y. Well, if you're only solving for y, if we're only caring about the variable y, then the 3x we can essentially just treat as another number. We can just do things to it that we would with regular numbers. And what I mean by that is when we try to isolate 6y by itself, we're just going to move 3x over because we don't care about the 3x. We're not trying to solve for x, we're trying to solve for y. So if I say again, solve for y, and I'll write it out one more time, solve for y. Okay, so our steps are still going to be exactly identical to what we were doing before. We check for fractions. Do we have fractions here? No. Okay, don't worry about clearing fractions. So now what I'm going to do is I'm going to say, okay, there's nothing that we have to expand or distribute. So I'm just going to try to isolate y by itself. And isolating y by itself means I'm going to move the 3x over to the other side. Now it's a positive 3x originally, so I'm going to subtract both sides by 3x. And we have 6y is equal to 9 minus. Now we say, okay, well, we're getting pretty close. Again, our goal here is we want to solve for y. So what's attached to y? Well, we have a coefficient of 6. It's being multiplied by 6. To undo multiplication, we have to divide. So when we divide by 6, we get y on the left side, and we get 9 minus 3x over 6 on the right-hand side. And we're almost done. We can clean this up a little bit and say, okay, well, we see that we have factors of 3 in all 3 pieces on the right-hand side. So I'm going to pull out a 3, and I'm going to say, okay, well, y is equal to, if I pull out a 3 from the top, we're left with 3 minus x. And 6 is the same thing as 3 times 2. Right? And since we now have factors that are being multiplied, we can now cancel, right? The 3 on the top and the 3 on the bottom cancel, and we are left with y is equal to 3 minus x over 2. Okay, so the entire idea is the same. You're going to follow your same exact procedure. The only difference is you are only concerning yourself with one particular variable. The other variable can kick rocks, right? Where we don't care about it. We don't, whatever happens to it happens to it. It doesn't matter. We're still trying to isolate, in this case, y. Okay. All right, let's look at one more example together, and then you will have your last classwork, and then that'll be it for today. So let's see, we'll clear this. Okay. In physics, so this is a word problem. I hesitate to write it all out, but I'll write the important parts. Feel free to rewind the video as many times as you need here. In physics, force is equal to mass times acceleration of the object. If the force was 24 and the mass of the object was 9, find the acceleration of the object. So let's break it down. I said if in physics, force is equal to mass times acceleration. So force, that's an F, not an E, I promise. F is equal to mass times acceleration. And I'm just using M for mass, A for acceleration, okay? And we are given that the force is equal to 24. The mass of the object is equal to 9, and we have to find the acceleration of the object, right? So this was all given to us, and our goal here, you should always try to write your goal. We're trying to find acceleration, okay? Now, just to really hammer down on the fine details here, in general, if you did take a physics class or if you have taken a physics class, what I just wrote isn't technically correct because normally you would have units attached to the numbers. This is just an algebra course, so I'm not putting units. Normally you would have like meters per second. You would have for acceleration, it would be meters per second squared. Don't worry about that. I'm not concerning myself with that. Right now, we're just worried about solving for a particular variable with numbers, okay? So I don't care about the units right here. Okay, so we have force is equal to mass times acceleration, and we want to find acceleration. So what do we do here? Well, if A is the variable that we care about, we say, okay, what is happening to A? We want to isolate for A. So to isolate for A, we're going to move mass over to the other side. And by doing so, we're going to divide out mass from both sides, right? So force is equal to mass times acceleration. This is the same thing as if we divide by m on both sides, force over mass is equal to acceleration, right? And now all we have to do is, okay, we now have an equation that we can work with. Acceleration is equal to force over mass. We're just going to plug in the numbers that we were given, right? 24 is force, 9 is going to be our mass. So A is equal to 24 over 9. And we say to ourselves, okay, great, 24 over 9. Both of them are divisible by 3, right? So I can pull 3 out. 3 times 8, 3 times 3. We know that one factor pair of 3 is just going to cancel, so that's gone. And we're left with 8/3. So acceleration is equal to 8/3. And that's your final answer. Okay, so the entire idea here is we were just trying to set up our equation such that we only care about the one particular variable, and then we solve for our unknown by plugging in our numbers. Okay, so go ahead and now that we've done this one classwork assignment, this example, try the last classwork assignment. It might be a little challenging because there's a lot going on there. There's a lot of information, but try it and then we'll talk about it in just a second. Okay, so again, hopefully not too bad, but I know that there's a lot of moving pieces here, so let's try to break it down. It's another word problem, and I'm not going to write the entire word problem out because this one should be right in front of you on your classwork, but I will read it for the purpose of reading it. So we have Sarah purchases subscriptions to streaming services, don't we all? For the first month, Sarah only buys into Netflix. For the next 3 months, Sarah buys subscriptions to both Netflix and Hulu. Assuming the cost of Netflix is $10 a month and Sarah has spent a total of $76 at the end of 4 months, how much is the Hulu membership per month? Okay, like I said, a lot going on here, right? It helps when you're discussing word problems and you're trying to set up an equation to just list out your knowns and your unknowns, right? You list out your knowns and then you list out your goal. So what is our goal here? Well, our goal here is going to be how much is the Hulu membership per month, right? So what I'm going to write here is I'm going to write an H, and I'll even write it in green because we all know Hulu is green, right? So we'll write Hulu, and that's our goal. We're trying to figure out how much this is per month, okay? Next up, we're going to write out our knowns, right? So in the very first sentence that we have information, we're told for the first month, Sarah only buys Netflix. And then for the next 3 months, Sarah buys both, right? So that tells us that Sarah has had Netflix for a total of 4 months, right? If she had it for the first month and then she had it for the next 3 months, then she's had Netflix for a total of all 4 months, right? And the variable that I'm going to use to denote this is an M for month and then a subscript of N for Netflix, right? You don't have to use these variables. I'm just doing this so I can keep track of my information. I'm also writing this in red because Netflix, commonly noted as red. So, maybe do things to help you keep track of what's going on. So she has had Netflix for 4 months. Okay, what's our next piece of information? Sarah buys, in that same sentence, for the next 3 months, Sarah buys subscriptions to both Netflix and Hulu. So that also tells us that Sarah has had Hulu for 3 months, right? Because it says for the next 3 months, right? And she didn't have Hulu for the first month. Okay. And our last piece of information here is assuming the cost of Netflix is $10 a month. So the cost of Netflix is $10 a month. How much is the cost of Hulu membership if she spent a total of $76 at the end? And so I'm going to go back and say total is 76. Okay, so now we have a bunch of variables, right? And we have all of our knowns, and we're trying to figure out, okay, how do we set up our equation based on our known values, based on our the information that they gave us, so that we can solve for this, right? So, sorry, 1 second, I have to cough. Okay, there we go. So what we have to do here is we have to set up a linear equation such that we're going to eventually be trying to solve for our goal, right? And our goal is this guy here, the price of Hulu. Okay, so now what we're going to do is in setting up this equation, we're going to say, okay, well, what makes sense here? Well, if I had Netflix for, say the price of Netflix hypothetically was only $5 and I had it for 2 months, right? It's $5 per month and I had it for 2 months, so it would be 10 months, or I'm sorry, $10, right? And that intuitively makes sense to you. So what you're doing is you're taking the price and multiplying it against the number of times that you've been charged that price. So what we're essentially saying is, okay, well, that means that we have n times mn, or m sub n. So we have the price of Hulu times the amount of months that we have been charged for Hulu. And also, we have the same thing, but for Hulu, right? And I think I just said, I meant to say Netflix. I'm so sorry. So we have the price of Netflix times the number of months that we were charged for Netflix. And now we're going to have the price of Hulu times the number of months that we've been charged for Hulu. And in total, that should give us the total value, right? That should give us the exact number that Sarah has spent at the end of 4 months on her streaming services. So now what we're going to do is, okay, we have finally set up our equation, right? We have n times m sub n plus h times m sub h is equal to our total. So now we just have to plug in the information that we were given here. So if n is equal to 10, we're just going to put 10. And we know that she's had it for 4 months, right? $10 times 4 months. And over here, we're going to bring down the plus sign. We still don't know what h is, right? But that's what we're trying to solve for. And we know that she's had Hulu for 3 months. And this is all going to be equal to 76, right? The total dollar amount that she spent at the end of this is $76. So now all we have to do is just treat this like a normal linear equation, right? So now 10 times 4 is 40. We're going to go ahead and distribute or expand the pieces that we need to expand. Plus, and now we don't know what h times 3 is, but we can just say 3h. That's our variable that we're solving for, is equal to 76. And at this point, I'm just going to stick to black ink because I think that we all understand what's going on here now. Okay, so now we have 40 plus 3h is equal to 76. Well, now we just have to isolate our variable, right? We have to isolate the h. We have to isolate the price of Hulu. So in doing so, we're going to move 40 over to the other side. We're going to subtract 40 over. So to subtract 40, we subtract 40 from both sides. We're left with 3h. And when we subtract 40 from 76, we're left with 36. And now this part's pretty easy, right? We just have our variable h times 3. So to undo multiplication, we divide by 3. So h is equal to 36 over 3, which is 12. So what have we just found out? We found out that the price of Hulu, according to this example, is $12 per month. And that's it. So the hardest part of this whole thing was probably setting up this equation here. But you just set it up so that it makes sense, right? You have the price of something and how often you're being charged for it, plus the price of the other thing and how often you're being charged for it, and that would be equivalent to your total. And obviously dissecting the information, extracting that information, maybe not be the easiest thing, but hopefully this should start giving you some practice. Word problems aren't going to be something that we focus on in this class, but it is good to be able to, work with them sometimes, to be able to dissect the information and apply it in real time. Okay, so that's it for chapter 1.1, which is the linear equations in one variable. If you guys have any questions, please feel free to ask me. Homework will be up very soon to accompany this video. And yeah, that'll do it. So enjoy the rest of your weekend, and I will talk to you all on Monday. Have a good one, guys.